Today, he's talking to us at the call to arms. You almost certainly have an ARM microprocessor or a dozen or so in your pocket at this moment. The ARM microprocessor dominates the world of both mobile and embedded computing, and over 2 billion, that is not a typo, over 2 billion ARM-powered microchips have been manufactured to date. But the interesting thing is that the origins of ARM can be traced back to a small UK supplier of desktop machines called Acorn Computers Ltd, which some of you remember in the early 80s, for whose staff the original ARM was the first attempt at designing a microprocessor. A key person in all that process was, of course, Steve Furber. So without more ado, can I invite you, Steve, to give the Dickinson Memorial Lecture.
Okay, I'll just clean up the screen a bit. And well, thank you very much for that introduction, Jonathan. I just have to correct you on one fact. The number of ARM-powered microchips sold to date is not 2 billion, it's 200 billion. which you think, if you think of that in terms of the number of computers per human on the planet, it's a scary number. Okay, as you heard in the introduction, I'm Steve Furber, and for the last 30 years, I've been in the ICL chair at the University of Manchester, but I spent the 1980s with Acorn in Cambridge, and as you heard, I was involved in the development of the first ARM processors. And today I'm going to muse a bit about the origins of the ARM and where it has led to today, exemplified by the introduction last year of the Apple Silicon M1 powered Mac computers, one of which I'm using to deliver this presentation. What am I going to talk about? Well, when everything's working, this is an outline of my talk in 4 sections. So I'm going to start off talking about the ancient history of the time at Acorn. Then I'm going to say a little bit about my current research at Manchester, which is still very strongly connected with ARM. Then look a little bit about what we can learn from where ARM has gone in the 40 years since the first ARM chip, and then draw some conclusions. So, start at the beginning. And that's with little acorns. Where did Acorn come from? So the origins of Acorn can be traced back to a company called the Cambridge Processor Unit, started by Hermann Hauser and Chris Curry in 1978. And this company started off as a microprocessor consultancy, and the first contract the company got, which I had some involvement in, was developing a microprocessor-based controller for a fruit machine, of all things. This was the point in time where games machines and fruit machines were making the transition from electromechanical to electronic, and CPU Limited had a role in those early developments. This was a surprisingly complicated device involving 2 national semiconductor SCMP microprocessors and software to try and make this parallel system run coherently. We also had some involvement with the machine you'll see on the left. I don't know how many people recognize this. There are a number of people in the room nodding their heads. I think you have to be from a certain era. That's the Science of Cambridge MK14. And I actually assembled the first MK14 prototype on my living room floor and debugged some of the ROM code. And it was out of those seeds that Acorn developed. But at that stage, it was called CPU Limited. Then the following year, saw the introduction of the Acorn System 1, and this is where the Acorn name was used initially as a trading name. So the company was still called CPU Limited. The product was called the Acorn System 1. And again, you have to be of a certain era to recognize this and understand what you're seeing. But it was a 2-circuit board system. The top board had the keypad on, the bottom board had the microprocessor and most of the interfacing components. And this was a machine that you could program by entering your instructions in hexadecimal. So hexadecimal is a convenient shorthand for binary. Each hexadecimal symbol represents 4 bits of information. So effectively, to program this machine, you had to handwrite binary machine code and then enter it in with 2 key presses per byte into the machine to get it to run. And at the top of the machine, you can see a hexadecimal display. So the machine would respond and the program would control the display to give you its output in hexadecimal. And so in those days, to use this sort of computer, you had to be reasonably fluent in hexadecimal, which is base 16 arithmetic, both for programming and for understanding the output from the system. Now, this was a fairly simple system. It was about the same period as the Sinclair ZX80, and there was quite a lot of competition between Acorn and Sinclair. Acorn was not Acorn yet, but the company, partly, of course, because Chris Curry had come from Sinclair's business and joined with Hermann Hauser to form this competing company. And one of Clive Sinclair's proud boasts with the ZX80 was that you could use it to control the nuclear power station. Now, I suspect that wasn't entirely accurate, but we had a counter to that, because I don't know who recognizes this. Who can tell me where that picture comes from? No. Everybody's remaining silent in the room. I don't know how many people online are trying to respond to this question, but you're all muted, so I can't hear you at the moment. The answer is that that is a picture from, I think it was a BBC television series called Blake's 7. And if you remember Blake's 7, it was stories about the crew of this 22nd century cargo ship, which was flying around the galaxy, doing whatever cargo ships do. But at the heart of this 22nd century spaceship, there was a computer. And in the middle of the computer there, you can see an Acorn System 1. And Sophie Wilson, who designed the System 1, always said when the actors went up to that and pushed the buttons, they actually pushed the correct buttons to start it running. So Sinclair may have been able to control a 20th century nuclear power station, but the Acorn System 1 could control the 22nd century intergalactic cargo ship, and therefore was obviously superior. Now, Acorn used the System 1, which was a pair of standard size circuit boards to build a series of larger systems. And these were the systems 2, 3, 4, and 5. The base machine was the System 1. And these could be expanded into rack-based systems with, you can see at the bottom, each of those card slots contains a different circuit board with a standard backplane. So you could pick and mix from the various circuit boards. You could have things like display controllers, floppy disk controllers, EEPROM programmers, and a range of other components, and assemble some kind of control system. And these were quite expensive when you had them fully stacked. They were mainly used for things like research labs and industrial control. So they were professional users. But then Chris Curry decided that the company ought to appeal more to the home audience or the hobbyist audience. And so in 1980, the company, which I think by this time was actually called Acorn Computers Ltd, came out with its first home computer, which was the Acorn Atom. And you see here, this is beginning to look like what we know as a personal computer today. It's a box with a standard typewriter style keyboard on it. Inside that box, there's the computer and various peripheral devices. Its output would drive a standard television set at the time, so you could get a color display on your TV at home. And it came with a high-level language, BASIC. You could still program it in assembler if you were keen, but for the typical user, BASIC was a much more accessible way of telling the machine what to do. Now, if you read the small print on this slide, around where it says the price, £150, it also, plus VAT and P&P, of course, yes, so in very small print. But it also says above that, also available ready built. Okay, so what's being advertised there, the base price, is a kit. And you would get these machines shipped through the post, and you'd have a printed circuit board and all the necessary microchips and the cases and so on. And you pick up your soldering iron and assemble it. And like the System 1, this initially was sold as a kit, but it rapidly became clear that the market for machines such as this was rather larger than the number of people who knew which end to pick up a soldering iron by. I think we've all picked up a soldering iron by the wrong end only once, though. It's not pleasant. One thing I remember from this era was a frustrated customer who'd sent the computer back. It didn't work. They'd received it. They knew that heat was bad for microchips. So they very carefully, instead of soldering the chips in, they glued them in, but it still didn't work. At that point, I think we realized that possibly ready built was the way to go. And that is the way Acorn's business moved after that experience with the Atom. It was quite an advanced machine. You could actually connect it to a computer network. You could add bits inside for its Ethernet networking. And that was the very early days of computer networking on the Acorn Atom. In fact, you could add so many things inside that the linear voltage regulators that generated the right voltages for the components inside would get so hot that they would melt the solder with which they were attached to the circuit board. And as the circuit board was upside down in the case, they would then drop out. And had quite a lot of incidents of voltage regulators dropping out. So quite a lot was learned from that. So following on from that, and I was not personally directly involved in the Atom. Nick Toop was the lead engineer on that particular project with Chris Curry. But the company started to think about what sort of machine it should develop next. And this is a picture from the development of the concept to follow the electron, which was imaginatively called after a slightly larger subatomic particle, the proton. The interesting feature of this photo is that that's me, sort of closest to camera in the middle. And I like this photograph because it shows that there was a time when I had hair. Few people can remember that. And the Proton was based on very similar principles, but I guess most people are familiar with the story that partway through the thinking about the Proton, Acorn got to hear about the BBC's interest in having a computer developed to go with the series of computer programs. And that, of course, then led to the BBC Microcomputer, which was launched in 1982, the year my first daughter was born. Now, the BBC Micro was not the full Proton implementation. Proton was being thought about as a dual processor with the 6502 front end and quite a flexible set of back end options for the main processor. But for cost reasons, the BBC Micro started life as just the front end processor. And then the second processors were added as optional add-ons, which of course most users weren't interested in, but it did provide quite a good development basis for things that happened in the future. Now, this picture is, of course, the Acorn marketing department's view of the BBC Micro. It's not quite how I see it. I tend to see it more like that. My main involvement in the BBC Micro was the logic design of the main circuit board, which is what you see here. And what you're looking at is the printed circuit board that's inside that box. And on that, there are a whole lot of these things we call microchips. In fact, if the board is fully populated, which this one isn't, you can see there are some components missing at the top left. I think they are probably the optional network add-ons that you could add later if you wanted to. Though, if everything was fully populated, there would be 102 microchips in this board. And in the early 80s, when the BBC Micro was designed, there were many companies in the UK and elsewhere in the world designing personal computers. And the way these were designed was that components were selected that came off the shelf from the various semiconductor manufacturers who produce such things. And these are then designed into a circuit and assembled into a circuit board. Software is developed, which usually requires more effort than the hardware. And then you can have a product to sell. Now, as I say, these chips all look very similar, and they are principally off the shelf. One of the key chips here, which looks like several others, is the one in the middle, and that's the microprocessor. The BBC Micro used the 6502, which is the same microprocessor that was used on the Apple II, the Commodore PET, and quite a number of other computers. It was a hot favorite at the time because most of the 8-bit microprocessors were pretty similar, but the 6502 was quite a lot cheaper. And therefore, it found its way into a lot of those early computers. The 6502 was standard off the shelf because the BBC Micro came a little bit later than, for example, the Apple II. We ran the processor at twice the frequency, so it had twice the compute throughput of the Apple II, but otherwise these machines were basically quite similar. However, not quite all the chips on the BBC Micro were standard off-the-shelf parts. There were 2 chips on here, smaller ones than the microprocessor, that were bespoke chips that were designed for the BBC Micro. And these used a technology from Ferranti's in North Manchester called the uncommitted logic array, where they developed a standard base chip, but all the wiring was configurable by the customer. Not after purchase. This was the last level of wiring was put on in the final stages of production, but the customer could design these. And those 2 chips replaced about 10 or 20 of the standard parts. So what those chips did could be done with standard parts, but it would take 10 or 20. One of those is the video processor, and the other is the serial processor. So without those chips, this circuit board would have had to be quite a bit bigger to hold maybe 130 microchips, and then it wouldn't have fitted in the box, and there'd been all sorts of problems. And those chips were my introduction to the design of microchips, and that really set the direction for the rest of my career. So the BBC Micro has an important role to play in the way my career has developed. Now, the BBC Micro, as you know, was quite successful. When Acorn was in discussions with the BBC at the outset, the BBC reckoned that on the back of the programs they planned to produce, Acorn might expect to sell 10,000 or so of the BBC Micros. And that was good business for Acorn. 10,000 machines, was comparable with Atom sales. But of course, it turned out to be a hopeless underestimate. And ultimately, the BBC Micro sold about 1.5 million boxes rather than 10,000. So in the early 80s, nobody really anticipated the wide public demand for computers once they became reasonably accessible. And it took everybody by surprise. And companies struggled to keep up with demand, to the point where the BBC Micro was quite often sold by retailers at zero profit margin because they could make a bit of money on all the software and ancillary peripherals that went with it. So they were prepared to sell the machine at zero profit margin. Now, where did the machine end up? Well, it had a major role in school computing. Large numbers of schools used the machine because it was backed not only by the BBC's computer literacy project, which was the reason that it was set up as the BBC Micro in the first place, but from 1982, the government had a Micros in Schools scheme, and they were trying to get computers into all schools across the country. And that gave Acorn a significant position in the education market. The scheme, I think, subsidized the purchase by schools, not just of BBC Micros, but also Sinclair Spectrums and Research Machine 380Zs. But the BBC Micro got by far the biggest take up in that particular business. And the people paying the rest of the money alongside the government money were typically local education authorities or parent-teacher associations. So the machine was in widespread use. And of course, the Micros in Schools scheme was political. So just occasionally we had to put on a suit and be visited by ministers. Again, you have to be of a certain age to recognize the minister in the picture. In fact, you probably have to be of a certain age to recognize anybody, because I'm not often seen wearing a suit. I'm the quiet one in the background, and Chris Turner, who is Acorn's chief engineer, is at the front with Kenneth Baker, who's holding the BBC Micro lid, and Hermann is in the center background, and Chris Curry to the right. So the BBC Micro established Acorn in a very strong position in the computer market, particularly, of course, in the UK, but also in some international markets. So the Micro sold quite well in Australia, New Zealand, the Netherlands, Germany, but it never really received global attention. And an attempt to set up a sales division in the USA was one of the reasons that resulted in Acorn getting into financial difficulties in a couple of years later. The other reason, of course, was the difficulty in 1983 of manufacturing enough electrons to meet market demand. And then in 1984, being able to manufacture far more electrons than there was market demand for, because it was a year too late. And those two things combined caused Acorn to get into difficulty. But following the success of the BBC Micro, at Acorn, we started to think about what we could do to follow on from that machine. And we looked at the various processor options that would represent a significant upgrade on the 6502. And they were generally 16-bit microprocessors, such as the Intel 8286, the National Semiconductor 16032, which later became 32016, the Motorola 68000, and so on. And we were not very happy with the characteristics of those microprocessors. And the two things we didn't like about them were, Firstly, they didn't make good use of the memory they were connected to. We'd formed the view that the thing that affects computer performance most directly is the available memory bandwidth that the processor can draw upon to fetch instructions and move data around. And those 16-bit microprocessors were slower than the commodity memories at the time. And the second issue that we didn't like was that those 16-bit microprocessors didn't have a very good real-time performance. In fact, they were worse than the 6502. By real-time performance, I mean an ability to respond to interrupts very quickly. The BBC Micro used very rapid interrupts to handle things like data transfers from floppy disk drives and so on. And the 16-bit microprocessors were not as fast. And while we were thinking about what to do, Hermann put some research papers from the west coast of the USA on our desks. And the classic one that we saw was the paper shown here with the title, "The Case for the Reduced Instruction Set Computer." And this was written by Dave Patterson and Dave Ditzel. And it was based on research carried out by a postgraduate class at UC Berkeley, led by Dave Patterson. And they were arguing that actually the 16-bit microprocessors that were coming out were not optimal when you look at what's best for a microprocessor that you want to put on a single chip. The 16-bit micros were largely based on the kind of architectures that had worked well in mini computers in the 1970s. And those mini computers were made of many separate components, and they had quite complex instruction sequences encoded into ROMs and other sorts of memory chips. But when you try and push everything onto a single chip, the overhead of those complex instructions becomes very significant and compromises what else you can do on the chip. And so the idea of the reduced instruction set computer was to simplify at the level of the instruction set architecture and use the silicon resource to do things that have more benefit for performance than complex instructions, of which the classic example is what's called pipelining, where a processor, instead of fetching an instruction, decoding it, executing it, and finishing it, and then fetching the next instruction, it works more like a production line. So it fetches one instruction, and then while it's decoding that, it fetches the next one, and then it's executing the first while decoding the second and fetching the third. Okay, so it's a sort of small production line, and that pipelining approach effectively increases the performance, the throughput of the processor by a factor 2 to 3. And that's a much bigger benefit that you can get from implementing complex instructions. So that gave Acorn the idea that it might design its own processor. Now, this was a rather crazy thing for a company such as Acorn to do. Microprocessors were designed by large semiconductor companies with teams of hundreds of engineers, and we talked to lots of them. They took many years to get their microprocessors right. They went through about 8 revisions to get the bugs out. And it was a large, complex, and expensive job. But this reduced instruction set computer idea suggested to us that we could simplify the whole thing using the RISC concept. And with a much smaller team, we could build something that would overcome the problems we'd seen with the standard 16-bit microprocessors of accessing memory bandwidth effectively and real-time response. RISC was good for that because all the instructions on RISC systems are simple. So none of them take very long to complete, and that's good for real-time response. And so this started in 1983 with Sophie Wilson playing with instruction set designs. I wrote, if you like, a hardware reference model, which today we call a register transfer level model, basically describes the processor as a set of registers that hold values and transfer information through adders or whatever to the next register and so on. And the tool we used for the reference model was BBC Basic. And the whole reference model occupied 808 lines of code. So it really was a very simple processor to put together. Today's ARM processors probably occupy 100,000 lines of Verilog. That's progress for you, apparently. So we developed this reference model, and that's allowed us to run programs under emulation, eliminate any bugs. And the software team working with Sophie wrote validation programs. So they basically wrote code which internally tested the functionality of every instruction and every variant of every instruction to check that the answers came out right. And then the reference model was translated into what we call block specs. And this would be a paper document of 2 or 3 pages that described the register bank or the arithmetic logic unit or the barrel shifter or the address register or something. So it was split into about 20 or 30 components, handed to the VLSI team that we had in the company with not enough to do at the time. So they were quite happy to play with this. And the thing was put together to form this thing that was called the ARM processor. And after about 18 months of work, we got the first silicon back from VLSI Technology Inc. We plugged it into a test card and had BBC Basic running that same day. And we then started a tradition, I think Hermann started the tradition at Acorn, which carried on to ARM, of when a chip first shows signs of life, a bottle of champagne is duly cracked, and there's a celebration, and a little note is written on the champagne label to indicate when this happened and what happened for posterity. And the last time I visited ARM and saw the bottle collection, it was a large field of champagne bottles at this point, but the first one was linked to this ARM chip. And the chip was called the Acorn RISC Machine. So its middle name is RISC, Reduced Instruction Set Computer, because it was clearly inspired by those ideas from the USA. It had Acorn on the beginning and machine on the end, just to make it sound right. And Acorn RISC Machine got contracted to ARM. And of course, ARM then later became a company in its own right. And the ARM name still survives today, although its origins are largely forgotten in the company's records. And this chip, which was simply called ARM, has since been rebranded ARM1 to differentiate it from its large numbers of descendants. And the first chip plugged in and ran code, and it did pretty much exactly what we wanted to. There's one story that's become legendary of when we tested the power consumption of the chip. It appeared not to require any power. We intended the chip to be low power because we needed to put it in a plastic package, because plastic packages cost about 50 cents and ceramic packages cost about $20. And to go in a plastic package, we had to keep the power consumption under 1 watt. And the tools we had to manage the power consumption were a bit sort of Victorian engineering. And so the chip ended up coming in at a lot under a watt. But the first time I tested the power, I did the usual thing of disconnecting the power, putting an ammeter in series with the power, turning the processor on, making it run some code, and then looking at the ammeter. And the ammeter said 0. Okay. Now, it wasn't really using 0 power, but actually I had failed to connect the power back onto the chip. So it was drawing no current from the power supply. What it must have been doing is there are various inputs to the chip, and those inputs were driven by other chips, and they have protection diodes on so that they don't get broken from electrostatics when they're handled. And those other inputs must have been supplying enough power in through the protection diodes to enable the chip to run. That's become a kind of early ARM legend that it required zero power. In reality, when it was working hard, it consumed about 1/10 of a watt. So, as I say, we were well under the 1 watt target, and there was no problem continuing with plastic packaging. Now, much later, Hermann was asked to account for the success of the Acorn team, none of whom had had any involvement in processor design before. So we were doing it, sort of making it up as we went along. And he credits the ARM team with having 2 advantages over the semiconductor teams developing microprocessors in the big semiconductor companies at the time. And the first advantage he generously gave us was that we had no people, because Acorn was a small company. Even at the peak of the BBC Micro, it was a total of about 400 people, I think. And we had a team of sort of order 10 or a dozen to work on this project, rather than the hundreds that you typically find in industry. And the second advantage he gave us was that we had no money. Now, these, of course, are rather oversimplifications of history, but there is some truth in both of them. And the very small team did mean that simplicity was an imperative throughout the design process. And the RISC philosophy, of course, contributed a lot to enabling us to keep it simple. But that simplicity had to keep coming back in when we made other design decisions. And the very limited budget meant that most of the design and development processes had to be homegrown. So it was all done using very familiar tools. I've already mentioned BBC Basic. And so we were not having steep learning curves in coming to terms with large, complex external tools. So there you are, 2 advantages: no people and no money. That's something to learn at engineering companies. And I mean, I do believe that simplicity is a huge merit in engineering. I've come across many times engineers who are measured on their productivity. So if you're designing a chip, how many gates do you design per week? Whereas my engineers, I was more interested in how many gates they took out per week, which is negative productivity by standard measures. But actually, I think it's even more valuable than adding more gates. So where did this all go? Well, in 1990, that was the year I left Acorn to move to the chair in Manchester, just before Apple came knocking at the door of Acorn saying they wanted access to the ARM to use in their Newton product. And they were knocking on an open door because Acorn was finding it increasingly difficult to support the costs involved in maintaining processor development in-house. So they were quite keen to share that cost. And Apple proposed a joint venture to Acorn, and that joint venture was set up and became ARM Limited. Now, at that point, the Acorn in Acorn RISC Machine was cunningly changed to Advanced, so it became the Advanced RISC Machine at that point. But a few years later, they dropped the expansion of the acronym altogether. And today, I think the company logo has even abandoned the capital letters that imply an acronym. So they're now lowercase ARM if you look at their current logo. And this joint venture was set up. I think what's interesting, of course, is that, again, to a modern audience, most of them have never heard of the Apple Newton. I guess most people in this room have been around long enough to have heard of it. It was an early attempt at pen-based computing about 10 years before the iPhone, a bit more than 10 years. And really the technology was not quite ready at the time of the Newton. So the Newton as a product did not succeed, and Apple dropped it. But but it was vital to the survival, or in fact, to the establishment of ARM as a company. And then, as today, the Apple brand was huge in the computing business. And so ARM, having Apple as a customer, opened many other doors for them, and their business was established. And by the time it was becoming clear that the Newton was not going to succeed, it didn't matter, because ARM had managed to open enough doors to become safely established. They were also quite fortunate with their timing. They were formed in 1990, and it was in the 1990s that people started talking about systems on chip. And the idea of a system on chip is that you don't just have a chip for your processor and a separate chip for your memory and another chip for your peripheral. You put everything together, or at least as much as you can fit, onto a single chip. So it literally is a system on a chip. And the reason it started in the 1990s was because the number of transistors that were available on a chip was more than the number required for just a processor. And so you could get most of the system functions on the same chip, usually apart from memory at that point. Most of the memory would still be off chip, but all the other functions could go onto a chip. And ARM had an advantage here because, compared with the competition in the system on chip business, the ARM processor was small and power efficient. And if you have a small processor, and the example here shows the processor sitting at the top left corner of that chip, you have more room for the other stuff. So you can integrate more of the system onto the microchip if the processor occupies less of the chip area. And the real breakthrough for ARM came in the mid-90s when they won the contract for the chips to go in the Nokia mobile phone processors. Again, if you're of a certain age, you will remember that in the 90s, Nokia was by far the world's biggest manufacturer of mobile phone handsets. And so winning the Nokia business was huge and effectively established ARM as the de facto standard in the mobile phone business. And that's a position they hold right through to today. Pretty much every mobile phone now uses some variant of the ARM processor. So if we come right up to date, as I said in the introduction, the number of ARM-powered chips manufactured to date has now passed 200 billion, which is a silly number. I don't know where they all are, although I'm aware that I've got several tens about my person most of the time. They're all over the place. And ARM has become hugely dominant in the mobile and embedded business. And we'll come back to look a little bit at where that's got to later. But I wanted to move on to my second topic, which is describing the last 20 years of my research at Manchester, which is still linked to ARM. Throughout my time at Manchester, I've had active collaborations with ARM in various research activities. And the one I want to talk about is the one to do with building brains. And this grew out of a frustration on my part with the fact that although since I was initially involved to the end of the 90s, processors had become hugely faster, there were still things that humans, even young humans, 2-year-olds can do that we struggle to make our computers do. And so I became interested in trying to understand what are the similarities and differences between how we build computers and what we know about brains. And of course, the first thing you learn when you look into brains is we're still a long way from having a satisfactory explanation of how our brains work. And that's going to persist for some time. But interest in brains is not new. This lady is quite famous in the computing business, Ada Lovelace. She's known for working with Charles Babbage with his very early mechanical computers in Victorian times. And she wrote copious notes, most of which are in a library in a college somewhere in Oxford. But among those notes, as well as talking a lot about algorithms and computers, she talks about her interest in brains. And she says, I have my hopes of one day getting cerebral phenomena such that I can put them into mathematical equations. I hope to bequeath to the generations a calculus of the nervous system. Now, this was high ambition 200 years ago, and even today, if I wrote a research grant with those words in, it would be instantly rejected due to being hopelessly overambitious. We are nowhere near to having anything like an explanation of how the brain works as an information processor. But it's a challenge that people are increasingly facing up to, trying to make some progress in understanding brains. And if we come a bit closer to date, there's still a Manchester link. I live about 10 miles south of the city centre. If you know Manchester, I live quite near the airport. And only about a mile from where I live, there's this fairly nondescript semi-detached house, which has a blue plaque over the brick archway to the left where the blue arrow is pointing. And it says, Alan Turing, founder of computer science and cryptographer, lived and died here. And indeed, this was the house where Turing spent his last few years, because he'd come to Manchester to use the first machine to implement his big idea from the 1930s of the universal computing machine. And Freddie Williams and Tom Kilburn had built the first machine to embody that particular concept, and he came to Manchester to use it. Now, while he was in Manchester, he did various things to do with biology, but most relevant here is he wrote this seminal paper with the title Computing Machinery and Intelligence. And it begins with the words, I propose to consider the question, can machines think? Now, this was written in 1950, so 2 years after the baby ran its first program. And that early in the history of computing, Turing was already philosophizing about where this technology might go. And in this paper, he says that can machines think isn't a very good research question, and he turns it around into a test for human-like artificial intelligence, which he called the imitation game. And of course, that's the title that Hollywood picked on for its movie about Turing's life. He called it the imitation game, but we all simply know it as the Turing test for human-like artificial intelligence. And in this paper, Turing says that all he thinks a machine will need to pass his test, compared with the Manchester baby, is more memory. Now, the baby had 128 bytes of memory. To young audiences, I usually have to explain, yes, I do mean bytes, not megabytes or gigabytes. It had 128 bytes. And he reckoned all it would need to pass his test is perhaps a gigabyte. And he thought by the end of the 20th century, machines might have a gigabyte of memory. And that was a remarkable prediction, to predict from 128 bytes to 1,000 million bytes in 50 years. But it was accurate. I mean, it was about the turn of the century when a typical desktop PC would have about a gigabyte of memory. It would also be about 1 million times more powerful as a computer than the Manchester baby machine that Turing thought was quite powerful enough. But it would not pass his test. And this would greatly surprise Turing. And my personal view as to why human-like artificial intelligence has proved much harder to implement on machines than Turing and many people since Turing predicted is because we don't understand natural intelligence. And natural intelligence is grounded in the brain, and we don't understand the principles of operation of the brain. So I think Turing thought that intelligence was about logic, okay? And computers are very good at logic. So I can understand how he came to that conclusion, but it's now quite clear that intelligence is not about logic, or not only about logic. And it's about something different. And that's why I think it's important to put effort into trying to understand more about the brain. So the two questions that motivate my research, which I've been leading for the last 20 years, can the formidable computing power that's now available to us today accelerate our understanding of the brain? And as we understand more about the brain, can we feed that understanding back to build better computers? And the particular project that I've been leading for the last 20 years is called SpiNNaker, which is simply a compression of spiking neural network architecture, because the neurons inside each of our heads communicate principally with these things called spikes. Every so often the neuron goes ping, and everything you're thinking at the moment about what I'm saying or about what you had for dinner or whatever is some kind of pattern of pings flowing between the neurons in your head, to the best of our knowledge. So with this project, we set ourselves the challenge of putting 1 million ARM processors into one computer and connecting them so that they could support real-time brain models. Even with 1 million processors, it's clear you don't get close to the scale of the human brain. In fact, when we set out, we thought it might be about 1% of the human brain, or as I prefer to think of it, as 10 whole mice. With what we know now, I would say it's more reasonable to say we could probably support a single mouse brain on these 1 million ARM processors. The mouse brain is very like the human brain, but 1,000 times smaller, so it's quite a convenient reference point. We set about building this machine. We started designing the silicon. That was the core capability of my group, designing this special SpiNNaker chip, which has the features on it that enable us to collect all these processors together. Each of these chips has 18 processors on, and then we connect lots of them together to build the 1 million processor machine. And we have to be able to support real-time communication of spikes or analogs to spikes through the machine. So with that chip, with its 18 processors, we can tile a 2D surface, and the standard big SpiNNaker board has 48 of those chips on. So 48 times 18 is 864, so that's just under 1,000 processors on one of those boards, and we can assemble those boards. We have 1,200 in the Manchester machine, and we've been running, if you like, a neuromorphic computing service, a brain-inspired computing service on this machine since March 2016. It started off as 500,000 cores and then was doubled to the 4 million towards the end of 2018. And this is all offered as an open service under the auspices of the EU Human Brain Project. And through that, we accumulate quite a lot of users, and the machine works quite hard. It's not the only machine there is. We've been loaning and selling boards to other research labs around the world for the last 10 years. And that map, I don't think it shows all of the current boards, but you can see there's a reasonable global distribution of people. It's not the only neuromorphic computing platform. There are different approaches available from different companies and labs, but they're all experimental machines. And the sort of things you can do with that, with 1 million ARM processors, are obviously what it was designed to build, to support, which is models of brain. And we've spent quite a lot of effort on the cortical microcircuit. So the cortex is the outer layer of your brain. It's almost like a sheet that's kind of crumpled up a bit to fit inside your head, so it goes right the way around the outside of the brain. And it has a very regular microcircuit, which is structurally well understood, functionally not understood at all. Okay, so we know the structure, we can model it. The models reproduce measurements from the biological system. So when this model runs, it fires at the right kind of rates in all the different neurons and all the different layers. So it's capturing something of the biology. And it's much easier to interrogate a computer model than it is to interrogate the biology. Probing living brains is messy, difficult, and has many ethical issues surrounding it, depending on whose brain it is you're probing. If you can model this with a model that you're satisfied is close to reality, it's much easier to then ask questions about that model. And not only do the ethical issues get put aside, but it's practically much easier to get into this model. We still don't understand it, but I think there's a reasonable prospect that some understanding will emerge of how this cortical circuit works over the next 5 or 10 years. So that's the kind of thing I've been doing for the last 20 years. The SpiNNaker 1 machine that I talked about is now quite old technology, and we've also developed a 2nd generation chip, which has just arrived in our labs, and we're beginning to play with it. And this gives us about 10 times the functional density and 10 times the power efficiency. And we've developed this with collaborators at the Technical University of Dresden in Germany, and they have big plans to commercialize this once we've got through the research phase. So that's a quick overview of what I'm doing now. The other topic I wanted to talk about, because I think from the ARM history, we've now got quite a lot of data, is what's happened over the last 40 years of Moore's law. I think probably most people here will have heard of Moore's law. It was published in a paper written in 1965 by Gordon Moore, who was one of the founders of Intel, who observed that the number of transistors that Intel could fabricate on a chip was doubling roughly every 2 years. And he predicted confidently in 1965 that this would carry on for 10 years to 1975. But of course, it became the major driving force behind the semiconductor industry and has carried on for a lot more than 10 years, although it's now beginning to hit some real physical limits. But if we look at what that means in terms of the ARM, here are 2 ARM chips. They're 35 years apart, but I'm going to call that approximately 40 for the purposes of keeping the numbers simple. And the reference points are ARM1, the first ARM chip, first ran code in 1985, and the Apple Silicon M1, which is in my laptop here, which was produced 18 months ago now, I think. So yes, I think that's how long I've had the machine. I mean, when Apple put an ARM in that laptop, I had to get one. It was just something you got to do. So if you look at how that's turned out, doubling every 2 years, sounds like good progress. But actually, it's an exponential, okay? And if you do the maths, then doubling every 2 years means a factor of 1,000 every 20 years, right? 2 to the 10 is 1,024. And a factor of 1,000,000 in 40 years, which is roughly the gap between these 2 chips, give or take. And so how does reality bear up? Well, the ARM1 used 25,000 transistors. The M1 chip in this laptop uses 16 billion. Okay, so that's a factor of 1,000,000, give or take. So it's all true. You really can see Moore's law doubling, and a lot of people have difficulty grasping exponentials. I mean, this was obvious at the beginning of the COVID epidemic, all right, when the number of infected people was doubling every 3 days. That's a factor of 1,000 a month. It's the same arithmetic as here. It's a factor of 1,000,000 every 2 months. It's scary, and people didn't seem to understand that. Anyway, so what else can we look at? Well, how is this number of transistors, how do they get so many transistors on? And the answer primarily, you can see the M1 chip is a bit bigger than the ARM1, but not much. These pictures are roughly to scale. But the feature size, in other words, the kind of smallest thing you can draw on the ARM1 process is about 3 microns. That's 3,000ths of a millimeter. Whereas on the M1, the minimum feature size is about 5 nanometers. Now that has to be taken with a slight pinch of salt, but it's broadly realistic. And so if you take those two feature sizes, the transistors, the features have got 1,000 times smaller in linear dimension, so that's 1,000,000 times smaller in terms of area. And so that's how you get 1,000,000 times more transistors on a chip. You make them 1,000,000 times smaller, right? It's not magic. Well, actually achieving it is pretty close to magic. But that's what the industry has done over the last half century. And can this go on forever? Well, the answer is no, because in the silicon crystalline structure, you get about 4 silicon atoms to the nanometer. Okay, so a 5 nanometer feature is 20 atoms across. You can't get that much smaller. Now today, the quoted feature sizes for these processes are becoming a bit virtual, right? They don't quite mean what they used to mean, but even so, the principle is there. We're getting worryingly close to atomic scale. And drawing these features on the chip, and of course with many billions of transistors on the chip, how do you make sure they all work? Right? This is not easy, but of course it's hugely valuable. So a huge amount of investment is justifiable into doing whatever is possible on this front. A lot of people confuse Moore's law with performance. Moore's law was just about number of transistors on a chip, but actually the same process that delivers that number of transistors also delivers other benefits. So smaller transistors are generally faster, more efficient, and up to some point, and we've actually passed this point, cheaper than bigger transistors. And the history of the semiconductor industry is getting this sort of win-win of faster, more efficient, and cheaper as they invest in these smaller processes. And the thing that really controls how fast they can shrink has been how long it takes to get the return on investment from one process development before they move on to the next. And that's turned out to be quite short. And they've been able to sustain Moore's law and pay for it. The 1,000 times reduction in linear dimensions that we see here, including local wiring lengths, allows around 1,000 times increase in clock frequency and hence processor throughput. So the ARM on the left would run at about 5 or 6 megahertz. It would do 5 or 6 million somethings a second, whereas something is adding 2 registers together or moving something from memory, it would do 5 million of those a second. Today's M1 chip will do billions of those a second. And in addition to each processor being faster, you can use those transistors to put more cores on. So the M1 has 8 ARM processors on that chip, of which 4 are optimized for their performance and throughput, and 4 are optimized for their energy efficiency. So when the computer's not doing much, which I guess is current, although it is running Zoom at the background to send all this stuff out to the online audience, and that probably involves a bit of work. But probably it's mainly the efficiency cores that are running at the moment. And if you multiply all those things together, you can see that you get an increase in throughput with M1 compared with the original ARM of about a factor 10,000. So it's a lot of progress. And that's just the basic processor throughput. M1 also has quite a lot of accelerators for key specific functions for things such as image processing, video compression, neural networks, and so on. And when those accelerators come into play, you can see a lot more than that basic factor of throughput. So it's a formidable device. Another interesting comparison point is what's on the chip. And here, of course, ARM1 is just a processor, whereas M1 has all this other stuff in there. And with M1, they've also put the memory onto the same substrate. So it's not on the same silicon chip, but it's now very close. And this is a physical picture of an early ARM1 system. with 4 megabytes of memory distributed across 64 memory chips, so 64 packages on that board. And the M1 has 8 or 16 gigabytes of memory, now in 2 packages, and they are quite hard to see on this slide because they use the Hitchhiker's Guide black on black color scheme. If you remember that episode, the black button with the black writing against the black background, which when you push it, lights up a display which says, please do not push this button again. And nothing else happens. Anyway, the memories here are those 2 chips, and they are attached to the substrate. So when you look inside the box, which I've not done, you find the processor and all the memory is in a very small and compact unit. So again, you can see Moore's law in action here, though the density has gone up not by 1 million, but by a factor of 100,000. But with the sort of level of approximation we're using here, we can view that as roughly the same. Okay, so getting to the end now, I just wanted to summarize what we've talked about with a sort of fairly graphic illustration. And I'm an occasional Twitter user. My wife thinks I'm a far too frequent Twitter user. But on Twitter, it's become a common practice to make a point by comparing 2 illustrations showing how it started and how it's going. So that's how I'll conclude my talk. How it started was with the ARM1 and the early Acorn desktop products. The Archimedes machines, again, you see the red buttons on the keyboard, which indicate this is still a BBC badged machine of some sort. Red function buttons were always a hallmark of the BBC. And where's it got to today? Well, you've already heard the numbers. ARM is in everything. If you use Apple AirPods, which are things you stick in your ear, each of those things you stick in your ear has 4 ARM processors in it, and formidable computing power in those things. It's in watches. I have an Apple Watch, which does all sorts of things that watches aren't supposed to do. It's obviously in phones because that's where it established itself as a dominant force. It's also in the supercomputer shown in the bottom left of this slide. This is the Japanese Fugaku supercomputer, which is currently the fastest supercomputer in the world. And it's held that position now for a year or so. It uses a chip with lots of ARM computers on. It's not quite exascale in full 64-bit floating point arithmetic, which is the benchmark for high-performance computers, but it's not far off. And of course, it's in the laptop. And ARM processors are also in many other devices, such as the wireless routers that you use at home, probably in the TV that you use at home, and so on. So they are everywhere, and that's why the numbers have got to this formidable scale of 200 billion chips, ARM-powered chips shipped to date. So it's been a very successful story for British industry. It's been in the news a bit recently for some of the wrong reasons, but that's business for you and has little to do with the technology. So with that, I think I'll stop and thank you very much for your attention.
That's frankly amazing. So I'm a bit lost for words. Can I have the prerogative of the first question? You've been very self-effacing and modest. How did you get into computing at Cambridge?
Do you want to unshare?
Oh, do I want to unshare? I suppose if I can work out how to do it, I will unshare. I think that's the magic button, isn't it? Right. And now I'm seeing 76 people on Zoom. and a rather smaller number physically in the room with me. By the way, we have set this up so that people watching the lecture on Zoom should be able to ask questions. I see there's already some things in chat. I can't currently see what they are, but my assistant will work something out while I'm answering the question. So how did I get into computing? Well, I went to Cambridge as an undergraduate to what they call read maths. There's not much reading involved, actually. It's mainly working out things. So my first degree is in mathematics, and I have quite a long interest in aircraft. So I did a Ph.D. in Aerodynamics. And in the course of my Ph.D., I learned about a group of students who were starting a society, which they called the Cambridge University Processor Group. And these were students who built computers for fun. And my interest in flying, it sort of led me to the logic. I joined the University Gliding Club in my second year. And, you know, in a whole year of going out to Duxford every Wednesday afternoon, I think I chalked up 54 flying minutes in the glider. And I decided this was rather inefficient and I couldn't afford the time to carry on in my third year. But maybe building a flight simulator would be a good way to get back into flying, virtual flying. So my interest in computing kind of grew out of that. How would you build a flight simulator? So I joined the University Processor Group and built my own computer. I was buying microchips from California on a credit card, which was very scary at the time, and successfully getting machines to work. And then Hermann Hauser, when he wanted to form this company, CPU Limited, looked to the processor group as an obvious source of people with appropriate skills. And that's how I got drawn in. And then you've heard about the early Acorn products, the BBC Micro. And in some sense, for me, it came full circle when a particular program was launched at the BBC Micro called Aviator. Who remembers Aviator? It was a beautiful wireframe SpiNNaker Spitfire simulation. So you could sit in your Spitfire and take off and fly around. And it wasn't a war game at all. I don't think you even had guns you could use. I can't remember, but it did have a bridge. And one of the challenges was to fly under the bridge. And then when you could do that, you could fly inverted under the bridge, and then you could fly inverted under the bridge and do a loop around it. So in some sense, that closed the loop on my interest in virtual flying. But by then, I was drawn into the world of computing and stuck there, I think.
Thank you, that was absolutely fascinating. Can I sort of ask you to...
Yeah, how are we going to do this? We've got to, is this?
No.
No, not that. This.
I come here.
I think you probably need to come
Everyone's
around.
got to come here. It's scary experience. Hey, that was absolutely fascinating. So could I just ask you to sort of expand a bit on the sort of financial models behind all this? Because you sort of referred to the investment in companies, but you work in university. So how do the research affect the sort of funding and the sort of research you can do, and how's that then sort of marketed and commodified? And because these are large numbers when one is dealing with. So I'm just wondering how all the sort of university research councils business link together to produce all this wonderful technology.
Right. Okay, that's a complicated question about the finances of underpinning university research. Designing microchips has become very expensive because as Moore's law has advanced and there are more transistors available, if you want to design a state-of-the-art microchip, then the effort that goes into that design has been growing exponentially alongside all the other exponentials. One of which, of course, is the cost of a foundry to make chips. So if you want to build a factory to make microchips, you probably need $5 to $10 billion to start these days. But academic research funding is not of that order of magnitude. And so the funding to build the SpiNNaker machine, well, to design it and then build it, came from the UK Engineering and Physical Sciences Research Council, EPSRC, and that came in the form of a series of grants, of which the last one was what EPSRC then called large grant, which they no longer offer. But it was about, I think, 2.75 million, something like that. And that, the physical cost of building the million-core SpiNNaker machine was the order of £1 million. The cost of employing the research staff to design it was rather more than that, but not enormously more. So you can develop a microchip. You can't develop one that's right at the bleeding edge of the technology. So even when we chose the process technology for SpiNNaker 1 back in 2005, it was not cutting edge. It was a bit behind to make it much cheaper to build. So that's how we build microchips. The number of academic research groups that can do this successfully has been declining because of the costs. If you design a state-of-the-art microchip in industry, well, the reference point I have is in the 90s, there was a very successful entrepreneurial business model called a fabless semiconductor startup, where you hired a bunch of chip designers to design a state-of-the-art chip, which you then sold. And around 2000, the investment to break even of such a company went past the $100 million mark, at which point the venture capitalists get cold feet. So there's been very few instances of a fabless semi-startup succeeding since 2000, because it's just got too expensive. Designing something like the Apple M1 chip, I am guessing, I mean, I don't know the numbers, but I would guess they've probably invested the best part of $1 billion in that. Just the design. So it's now how you transfer from academic research to industry is a different problem, and most academic research, of course, doesn't transfer. And SpiNNaker was conceived as a research project. The platform is primarily of interest to researchers, so it's not a commercial venture. I mean, we have been supplying the hardware to 100 odd labs, but that's not a business, right? And we supply the boards primarily to increase the impact of the research, not to generate money. If the technology does get to the point where it has commercial viability, then from a university, you would go through the normal venture capital startup route and try and bootstrap something that way.
Steve, if you click on chat.
I have to find my mouse to do that.
So Frank, the Vice Chancellor is going to have a research proposal for $1 billion this year.
Oh, shall I just... Steve, if you can ask Chris to unmute himself and ask his question.
I can't actually see a Chris on here.
And those questions come to the chair, which is me.
I can see 4 things on chat. Yes, I could see that Rob Schofield recognized Blake 7 quite early in the talk. Yes. Okay, and then comments from Peter, but I can't see any questions.
Chris, you want to unmute and ask your question.
It's Simon here. I posted a question.
Okay.
All right, Simon.
Right. The question I posted was that, am I correct that the original Microsoft PC was built around the 8086 processor, which restricted the amount of memory it could address? The commercial pressures, i.e. Bill Gates, talked it up against the superior 6502.
I guess that's right, yes. I mean, all of the early 8-bit microprocessors were restricted to 16-bit address spaces, so a maximum of 65 kilobytes of memory. But towards the end of the 8-bit regime, there were many attempts to extend those memories. And Acorn was interested in the 65C816, if I remember the numbers right and in the right order, which was basically a 6502 with a 24-bit address space.
Yeah.
And there were a number of processors that came out with fairly contorted ways of increasing the addressable memory beyond the 64K limit. But the obvious thing to do was to go to a wider data path.
Sure.
And of course, in the end, Acorn never had any mainstream 16-bit product because it went directly from 8 with the 6502 to 32-bit with the ARM.
Sure. Thank you.
Okay.
Yeah.
Chris asked the question, you mentioned silicon several times. How do compound semiconductors fit in? I thought their performance advantages were necessary for the top-end processors.
Okay, so I'm not an expert in silicon or compound semiconductor device technology, but my understanding is that compound semiconductors are devices based on materials such as gallium arsenide and so on. And I think those technologies have specialized uses, but mainstream semiconductor is still basic CMOS on silicon. So I don't think there are any high volume mainstream computer products that aren't just a basic silicon substrate. I know that you, for example, can't generate light with silicon. The band gap is wrong, and I'm getting outside my area of expertise, so there's a risk I'm starting to talk rubbish. But so gallium arsenide is used for things such as semiconductor lasers. But processing large systems with billions of active components is still principally done on silicon using CMOS, to the best of my knowledge.
Okay, can I? Yeah, fire away, please.
Yeah, I had a question. Thank you, Professor.
Yes, I think questioners in the room have to come and position themselves near the microphone.
I'm interested in what you were saying about the Atom and using the Ferranti ULA and how the process of, I guess, customizing that fed into the experience of designing the first chips.
Okay, so Ferranti ULAs were used by Sinclair in one of the ZX machines, if not both. And by Acorn first in the BBC Micro, and then the Acorn Electron used a bigger ULA to really reduce the number of chips from 102 to about 14, if I remember right. So the Electron was almost an early system on chip attempt, except the processor was still separate. And your interest is in how did we do those designs? So I think they were done the way one does any sort of logic design. So you sit down and draw logic schematics. You have to know the technology you're mapping into. So if you're going to use TTL, you need to know the Texas Instruments Orange Book fairly well. If you want to design on a Ferranti ULA, then the only technology you get there are NOR gates, 2 input, 3 input, I think 4 input NOR gates. But a NOR gate is universal, as is a NAND gate. And the ULA was NOR gates because of the particular technology they used. And then when you have your circuit, you then have to lay it out on the chip. And for the BBC Micro ULAs, the Cambridge Computer Lab had developed some basic CAD tools that allowed logic designs to be laid out by hand. They didn't automate the layout the way things are highly automated today, but they would allow you to enter the layout and simulate it and check its functionality. And for the electron chip, we actually built some software on a BBC Micro that allowed you to do the layout by hand. It was tedious. It took a long time. I mean, the tube ULA, which connected the second processor, I remember was on a piece of transparent film. So you got the base left from Ferranti, and it was about 4 feet square. Okay, and so this was stuck on an office wall. Now, at that time, Acorn was in the old water softening station, and they built glass-walled offices, which worked quite well for this. So if you stuck this 4 foot square thing on a glass office wall, you could then get lighting and you could see through it. And then you could draw lines by hand. And there was only a single layer of metallization that you could use. There were polysilicon underpasses, so if you needed to get underneath another wire, you could find a convenient underpass, connect to one side, and then go off the other side. And I think the Electron ULA had about 2,000 logic gates on it, something like that. So it's quite laborious. In fact, I remember having very strange dreams because I was doing this so intensively at one point that it started getting ingrained in my head and coming out in odd nighttime dreams to do with layouts and underpasses and so on. But I mean, detail engineering tends to have that effect.
Well, I think that's a brilliant instance of real engineering, drawing on a glass screen in a converted building. That's what I call real engineering. We've had a fabulous evening, Steve. I'm still reeling with it all. I have one last very fortunate and enjoyable task, which is to present you with your Dickinson medal for giving the Dickinson lecture. So with our warmest thanks, I'm sure the audience here and online will say, give a generous round of applause for what's been a truly splendid evening and a memorable lecture.
Thank you very much indeed. Thank you.
And for that, and with that, I think we'll sign off to our online audience and thank you all for attending. You've been a bumper audience. Thank you very much indeed, and I wish you all well and good night.